In this video, we're going to work an array of example problems related to the fundamental theorem of calculus. So the problems are going to be related to either part 1 or part 2 of the fundamental theorem. All right, let's get started. Sketch the area represented by g of x, then find g prime of x in two ways. A, by using part 1 of the fundamental theorem. B, by evaluating the integral using part 2 and then differentiating. All right, let's first sketch the area that this represents. So we want to sketch t squared. Let's just start by sketching it in general. So t is equal to 0, t squared is equal to 0, t is equal to 1, t squared is equal to 1, minus 1, 1, 2, 1, 2, 3, 4, minus 2, 1, 2, 3, 4, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. 3, minus 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, let's connect these dots. All right, and so the function g of x is going to represent some area under the curve t squared, and that the area is going to be relative to x is equal to 1. So there's x is equal to 1. Now, the way we'll draw the diagram, we'll assume that x is greater than 1. So x could be just anywhere greater than 1. And so this is x. And so what g of x, the function g of x represents is this area. Now we can think about the idea of having x be less than 1, but if that's the case, then it still represents the area between the x value and 1, but it's just negative. So like if x was with x is equal to minus 2, then the value of this function is this area plus this area, but then with a minus sign up front. Okay, so now we want to find g prime of x in two ways. First, by using part 1 of the fundamental theorem. So what the fundamental theorem, part 1, states is that if you have g of x is equal to the definite integral from a to x f of t dt, then g prime of x is equal to f of x. Now, there is one requirement. The requirement is that the function f of t has to be continuous between a and x. But t squared is continuous over its entire domain, so there's no issue there. And so with that, we can say that g prime of x is equal to x squared. Okay, B. Okay, we're going to find g prime of x. To get g prime of x, we're going to evaluate the integral using part 2 of the fundamental theorem and then differentiate. So to evaluate this integral using part 2 of the fundamental theorem, we need to find capital F of t. Okay, so taking the antiderivative of t squared, that would be 1/3 t cubed plus c, but for the fundamental theorem part 2, we don't need to worry about the plus c. Okay, and so g of x is equal to, so this integral is going to be, so the antiderivative and then taken from x to 1. So this is 1/3 x squared minus, and then plug in 1 minus 1/3. So this is 1/3 times x squared minus 1. Okay. Okay, so now let's find g prime of x by just differentiating this. So 1/3 x squared, or wait, no, this should be t cubed here. So okay. All right, so g prime of x is 1/3 x cubed. The derivative of 1/3 x cubed is x squared. The derivative of 1/3 is 0. So there you go. All right, find the derivative of the function. What is the derivative of this function here? Well, fundamental theorem, part 1. We have the definite integral from any constant to the variable, and then just a function, dt. The only thing we need to check is this function continuous from any 0 to x? And so you can see, though, if x was negative, then we could have issues. So x could potentially be less than 0. You just have to look at it. But if we just think about x being greater than 0, there's no issue. And so g prime of x is going to just be equal to square root of x plus x cubed. Okay, similar problem, but now we've got a 5 here. Does the 5 make things different? No, the fundamental theorem part 1 goes, it's the lower limit is just any constant to the variable. So for any t that's greater than 5, is there continuity issues? And actually this doesn't matter even if t is less than 5. So even if s happens to be less than 5. So there's no continuity issues here. So you just g prime of s, it's f of s. Okay, here this doesn't match the form of the fundamental theorem because you've got the constant as the upper limit and the variable as the lower limit. But we know that we can easily switch this by just putting a minus sign out front and swapping the limits of integration. All right, so now what is this derivative? Well, if we think about going from 0 to x, is there any continuity issues? Well, yeah, so secant does have vertical asymptotes even when t or x is greater than 0. So you'd have to evaluate this to see what the domain of the derivative is. But in general, f prime of x, this matches the form of the fundamental theorem part 1. So you just do, it's going to be minus and just f of x. That's it. All right, how do we get h prime of x here? So this is a little different. This doesn't match the form of part 1 of the fundamental theorem. And so what we do here is we say u is equal to e to the x. And so with that, what we have is okay, so there's h of x, right? So we want to take the derivative with respect to x of this. Okay, now this is a function of u, right? This looks confusing, but this entire definite integral is a function of u. So with the chain rule, how do we take the derivative of a function of u? Assuming that u is a function of x, which we know it is. Well, okay, this with the chain rule, it's df du times du dx, right? It's just confusing because you see this u in this small spot, so it's easy to forget that this is a function of u here. So what is it? This is f. This entire integral is f. What is the derivative of this with respect to u? Well, now we can use the fundamental theorem part 1. The derivative of this with respect to u is natural log of u, okay, times du dx. what is du dx? It's e to the x. So e to the x natural log of u. Okay, now, but what is u? U is e to the x. So e to the x natural log of e to the x. Okay, now what is natural log of e to the x? That should be x, I believe. Yeah. So x e to the x. So there we go. H prime of x is equal to x e to the x. Okay. So to make this, let's try and get this as close to the form of the fundamental theorem as possible. So this is y is equal to, we put the minus sign out front and flip the limits of integration. Okay, so now we'll say that u is equal to the square root of x. And so what we've got is okay, so now this is y, so let's and so if this is a function of u, right? This is some function of u, and we're taking d dx of this function of u, so it's df du dx. What is df du? That's going to be minus u tangent u, minus u tangent u. Okay, times du dx. And what is du dx? What is the derivative with respect to x of the square root of x? That's 1 over 2 root x. So this is minus u tangent u okay. Now substituting the root x for u. Okay, the root x is canceled, so continue this over here. So we've got minus 1/2 tangent root x. And that's it. There you go. So y prime of x is equal to minus 1/2 tangent root x. Okay, now we're going to evaluate some definite integrals. And we're going to do this using the part 2 of the fundamental theorem. So we're going to get the antiderivative of the function and then evaluate the antiderivative at the endpoint, or the limits of integration. So we can separate this into 3 separate integrals. Okay, what is the antiderivative of x squared? So reverse power rule, 1/3 x cubed, right? What is the derivative of 1/3 x cubed? Bring down to 3. 1/3 times 3 is 1. 3 minus 1 is 2, so there you go. Okay, now this is going from 3 to 1. Okay, what is the antiderivative of 2x? Well, that's going to be x squared. Just like reverse the power rule, and this is, again, going from 1 to 3. Okay, well, we could do the antiderivative here, but we know from properties of integrals, before we even learned about the fundamental theorem, that this is a rectangle. That it goes from 1 to 3, and then the height is 4. But I mean, we can do the antiderivative as well. So this is going to be 4x. The derivative of 4x is 4. Okay, so now what we do is 1/3 3 cubed minus 1/3 1 cubed. Okay, now this is 3 squared minus 1 squared. Okay, now we got to be careful with this minus sign. We want to put a bracket, this minus sign in front of everything we're about to write here. So we've got 4 times 3 minus 4 times 1. Right? This minus sign is in front of all of this. Okay, so we can factor out the 1/3 here. So you've got 3 cubed minus 1 cubed. So that's 27 minus 1 plus 9 minus 1 minus 12 minus 4, okay? 1/3 times 26 plus 8 minus 12 minus 4 is 8. So it's just 26/3. Okay, what is an antiderivative of sine theta? Well, minus cosine theta. The derivative of minus cosine theta is minus sine theta, so we put a minus out front. And now, don't worry about the plus c though, right? We don't when it comes to evaluating a definite integral, we aren't concerned with the constant. Okay, now this is going from pi to pi over 6, so this is minus cosine of pi minus cosine of pi over 6. So you got to be careful here. It's minus cosine of pi and then minus cosine of pi over 6. You see? That's confusing. You evaluate minus cosine of theta here, and then you subtract that from minus cosine of theta evaluated here. So we evaluated minus cosine of pi here, minus cosine of theta here. There's minus cosine of pi. Subtract that from minus cosine of theta evaluated at the lower limit. Subtract that from minus cosine of pi over 6. Okay, what is cosine of pi? That's minus 1. Okay, let me verify that. So cosine of pi, yeah. Okay, now cosine of pi over 6 is root 3 over 2. Okay, minus root 3 over 2. So we've got 1 plus root 3 over 2. There you go. Okay. Cosecant t, cotangent t. Maybe we can simplify this. So cosecant is 1 over sine of t. Cotangent is 1 over tangent t, which is cosine t over sine t. So how are they expecting us to do this? I mean, we're going to learn how to find antiderivatives and integrate. That's what a lot of the upcoming chapters are all about. But okay, so cosecant, the derivative of cosecant or cotangent must be something that works here. So okay, let's do t dx cosecant x. Yeah, there you go. That's what we just had. That's 1 over sine is cosecant, and then cosine over sine is cotangent. So, yeah, the f of t here is minus cosecant t, because the derivative of minus cosecant t, or we'll have x here, is, there you go. That's 1 over sine is cosecant, cosine over sine is cotangent, yeah. So this is this is minus cosecant t and then at these limits. So, okay, now you just got to be careful with the minus sign. So you take minus cosecant t, but evaluate it at the upper limit, okay? Subtract that from now minus cosecant, and then evaluate at the lower limit, like that. So we'll do minus cosecant pi over 2 is minus 1, okay? And then minus, and we've got minus cosecant pi over 6 minus 2. See how the signs is really confusing. So this is minus 1 plus 2, 1. So this is equal to 1. Okay, we can separate this into two separate integrals. All right, x to the e. This is just the reverse power rule. It's kind of confusing with the e, but this is just the reverse power rule. So the antiderivative here is 1 over e x to the, and it would be, well, no, okay, it would be 1 over, so 1 over e plus 1 x to the e plus 1, right? Because, okay, if you take this derivative, use the power rule, you bring down the e plus 1, and so e plus 1 over e plus 1 is just 1, and then you're left with x to the, and then you subtract 1 here, so you're just left with x to the e, right? And then this is, you're going to go from 1 to 0. Okay, now the derivative of, or the antiderivative of e to the x is just e to the x. Okay, so, all right, we can leave the e plus 1 on the outside and now just evaluate this from 1 to 0 of the just x to the e plus 1. So you've got 1 to the e plus 1 minus, and then 0 to the e plus 1. Okay, now you've got e to the 1 minus e to the 0. All right, so here you've got just 1 plus e minus 1. So 1 over e plus 1 plus e minus 1. That's it. Okay, so here, you know, when I see a piecewise function, I'm assuming there's going to be a jump discontinuity, and remember, you can't apply the part 2 of the fundamental theorem across a discontinuity. The function has to be continuous throughout the entire interval. But we talked about it when talking about the definite integral. You can have a function that is integrable it's integrable even across a jump discontinuity, right? Like if you had like something like this, and so here's A and here's B, this functions, this is f of x, this is integrable from A to B. You can find the integral from A to B. It's the area under, it's that area. You just can't apply, you can't evaluate this and say the antiderivative of f of x evaluated at B minus the antiderivative evaluated at A. You can't do that. You would have to break this up and do the, and do that. So if this is C, then you'd have to do that. You'd have to first evaluate this definite integral and then add that to this definite integral with using the because in that case you have two separate definite integrals where the function is continuous across the entire interval. But let's see here. If so, at pi over 2, at the potential jump discontinuity, what sine of pi over 2 would be what? That would be 1. Cosine of pi over 2 is 0. So there is a jump discontinuity. So this is something like, all right, from 0 to pi over 2, the sine function does like that. And then from pi over 2 to pi, the cosine function does what? So this is like that, okay? And they're saying that this is defined to, it equals 0. You don't use sine of x when x is pi over 2, you use this value. So this is an open circle. This is closed circle. This is closed circle. This is closed circle. Okay. And so we want to integrate from 0 to pi, from here to here. And this is integrable. This is a jump discontinuity, but this is integrable. It's going to be this area minus this area, and so we see it's going to be 0 because like the sine and cosine are the exact same function, just shifted. So this is going to be 0. But just for future reference, what we could do is we could say, so all right, pi to 0 f of x dx, because you can't apply the fundamental theorem part 2 from 0 to pi because it's not continuous from 0 to pi. You'd have to break it up. So you could do 0 to pi over 2 sine of x dx, and then pi over 2 to pi cosine x dx. Now, this is a little confusing because the function, like, how are you going to evaluate the function at pi over 2, sine of x at pi over 2, because it doesn't exist there. Because the fundamental theorem part 2, if you read the fundamental theorem part 2, it's talking about how the function is not only continuous, but it's the closed interval. And this is not a closed interval here. It's open at the right endpoint, but this still works because you're just trying to get the area under this curve here. You can still, the meaning of the definite integral in this case is this area minus this area. So we can just, we'll evaluate, like, okay, the antiderivative of sine of x is minus cosine of x, okay? And so then we're going from pi over 2 to 0, and then the antiderivative of cosine of x is sine of x from pi to pi over 2. Okay, so we're going to evaluate this at pi over 2. And this is concerned with this curve here. But the function doesn't even exist at pi over 2. Well, no, I take it back. It does, but it's equal to 0 at pi over 2. So it exists at pi over 2 and it's equal to 0, but we don't want to plug the function value in here. So it's a little confusing. But we understand the problem is we want this area and we want to subtract that area. So all we have to do is do, so minus cosine pi over 2 minus cosine of 0 plus sine of pi minus sine pi over 2. So this is, so cosine of pi over 2 is 0. Okay, and then we're saying plus cosine of 0 is 1. So just 1. All right, sine of pi is 0. Sine of pi over 2 is 1. There you go. Okay, sketch the region enclosed by the given curves and calculate its area. So, all right, x is equal to 4. 1, 2, 3, 4. There's the curve x is equal to 4. Y is equal to 0 is the x-axis. And then y is equal to the square root of x. So that it's 0, 0. And then, so where does it pass through x is equal to 4? When x is equal to 4, square root of x is equal to 2. So it passes through right here. When x is equal to 1, it's right there. So, okay. So it's the region enclosed by the x-axis, that's y equals 0, x equal to 4, and the curve y is equal to square root of x is this area. What's that area? Well, that is, if we're going to calculate this area, that is, you go from the definite integral from 0 to 4, square root of x dx. Okay, what's the antiderivative of square root of x? So x to the 1/2, okay? So 3/2 minus 1 is 1/2. So we want to do 2/3 x to the 3/2. Because we bring down the 3/2, this goes to 1, and then 3/2 minus 1 is 1/2. Plus c, okay. But we're going to ignore the c, so okay. This is 2/3 x to the 3/2, and then from 4 to 0. So we've got 2/3 and then 4 to the 3/2 minus 0 to the 2/3. So that's it. Okay, so this is, you've got 4 cubed square root. So, okay, 2/3 and then 4 is 2 squared. So you've got 2 to the 6th. 6 divided by 2 is 3. So 2 cubed. So 2/3 times 2, 4, the square root of 4 cubed is 8. So this is 16/3. This is 16/3. Okay. Sketch the region enclosed by these curves. So y is equal to 0 and y is equal to 4 minus x squared. So this is a y is equal to 4 minus x squared. That's a parabola, right? That's a downward facing parabola that's been shifted up 4 units. So that's 1, 2, 3, 4. There's the vertex. And then, okay, so like 1, 1, 1. So it goes through here. 2, 1, 2, 3, 4. 2, 1, 2, 3, 4, like that. So like that. So they want this area here. They're looking for this. Okay, so what is that area? The area between the curve and y is equal to 0. That's going to be, you go from minus 2 to 2, 4 minus x squared dx. That's it. Okay, so we can separate this up into 2 separate integrals. Okay, so we've got 4x and then minus, this is 1/3 x cubed, like that. So you've got 4 and then 2 minus 2. Okay, minus 1/3, and then you've got 2 cubed minus 2 cubed. See? So that's, so 2 plus 2 is 4. 4 times 4 is 16, minus 1/3, and then 2 cubed is 8, minus 2 cubed is minus 8, minus 8, so plus 8. 16 minus 16/3. So 16 times 3 is 48. 48 minus 16 is 32. So this is 32/3. That is this area here. All right, find the derivative of this function. So we want to put this in a form where we can use the fundamental theorem part 1. And with the fundamental theorem part 1, we've got, one of these is a variable term and the other is a constant term. And so we can use that the property of definite integrals with like consecutive areas here. We can say, so we can say that, so if we go from 2x to 0, and then u squared minus 1, okay, and now we need to put the 0 here, and then 3x, then these are equivalent. These two are equivalent. And it all comes from this property. It comes from, you say, so a to c f of x dx plus c to b f of x dx is equal to, and then a to b f of x dx. And so you can, but the key is these numbers, it could be anything you want. It's not like these have to, like a has to be less than c and c has to be less than b. It's any numbers you want. And so if you compare these two, it matches up, right? The zeros are the same, and then you go from a to b in the final result. The zeros are the same, you go from a to b in the final result. You see? Okay, but the fundamental theorem, part 1, it has the constant as the lower limit. So this, we want it in this form. So we want to flip this. So put a minus sign out front. Okay, now we're getting somewhere. Okay, so now this is just a chain rule problem, but for each of these separately. So we just make a substitution. We can't use u this time, so let's just say a is equal to 2x. And here we'll say, well, I don't want to use a and a because we use a over here. So I'll say L is equal to 2x, and I'll say z is equal to 3x. So we've still got g of x because L and z are functions of x. And what we have is, so L to 0 and then z to 0. Okay, so this is some function of L, this is some function of z. And so we can just take d dx of this, right? So we're running out of room here, but okay. So g prime of x, start here, minus, all right, you do, it's d, so if this is some function of u, or some function of L, you do df dl, and then dl dx. And so what is dl dx? Let's just calculate that here. That's 2. Okay, what is dz dx? That's 3. So, okay, minus df dl. So that's going to be L squared minus 1 over L squared plus 1 times dl dx. Okay, plus, now this is some function of z. What is df dz? Okay, now what is dz dx? You see? So let me create some room here. So g prime of x is equal to, we've got 2 times 1 minus L squared over L squared plus 1 plus, then we've got 3 times z squared minus 1 over z squared plus 1. Okay, so g prime of x is equal to, all right, I'm going to distribute the 2 here. So 2 times 1 minus, what is L squared? 4x squared over 4x squared plus 1 plus 3. Okay, what is z squared? That's 9x squared. There you go. There's g prime of x. Okay, so similar idea as the previous problem. We know that we've got, so if we go from A to C, and then from C to B, this is equal to then A to B. So we want to create 2 integrals that have a variable term and a constant term. So we can do, so from x to 0, and then from 0 to x squared. Okay, now we can put a minus sign and flip this. Okay, so this, we don't need to use the chain rule. F prime of x here is just e to the x squared. Here we need to say, so u is equal to x squared. And so du dx is equal to 2x. So we've got, this is minus, so from 0 to x, okay. So now if we take f prime of x, we've got minus e to the x squared plus, okay, this is some function of u. So chain rule, this d of this function of u, du. So df du is what? E to the u squared times du dx. All right? Now, let's substitute back the u back in. So you've got 2xe, and this is x squared squared. So f prime of x is equal to minus e to the x squared plus 2x e x to the 4th. And there it is. There's f prime of x.